Chemical reactions are never instantaneous. There is always a certain amount of time needed for the reaction to occur. Sometimes this can be relatively short, and other times it can take much longer. How quickly reactions occur is known as the rate of reaction. Reactions that happen quickly are said to have a fast or high rate of reaction, meaning that the time needed to complete the reaction is short. There are several factors that influence the rate of reaction. For a reaction to occur, the particles must come into contact with one another. The faster the particles come into contact, the faster the rate of reaction. This is known as collision theory. Dissolving a substance into a solution affects how quickly the particles contact, because reactants are free to move around and near to one another. If all reactants are in the solid phase, then the reactants are not free to move around and so take longer to react. To demonstrate this, we tried two different ways to react lead nitrate and sodium iodide. In the first method, we mixed solid reactants, while in the second method, we dissolved both reactants into solution, and then mixed the two solutions together. The solids required 3 minutes and 20 seconds, while the solutions only required 1 minute to react. This shows that the rate of reaction was more than twice as fast when in solution. The effect of mixing and of dissolving solids into solution can be seen in washing machines. Liquid detergents are often preferred over powders because the reagents are already dissolved, which speeds up the reaction time in the wash. The washing machine also spins to ensure the reagents collide with the dirt. Another factor that influences the rate of reaction is particle size. Particle size refers to the size of the solid pieces of a reactant. When a reactant is in a solid state, molecules will stick together to form particles. The molecules on the outside surface of the particle are easily accessible for the other reactant, while the molecules inside the particle are not so easily exposed to the other reactant. When the particle size is large, a smaller proportion of molecules are exposed at the surface area, meaning that the rate of reaction will be slower than a particle of smaller size. Just like in the previous experiment, this is a part of collision theory, where the reactants must come into contact for a reaction to occur. To examine this, we conducted an experiment to react marble chips with hydrochloric acid to produce a gas. In the first test, we used regular marble chips with relatively large particle size. In the second test, the marble chips were ground to a powder, giving a smaller particle size. The large particle size marble chips reacted with the acid and inflated the balloon in roughly 2 minutes. The powdered marble, which had a smaller particle size, reacted with the acid and inflated the balloon in less than 10 seconds. In this experiment, the powder reacted in a time that was under 10% of the time taken to react the larger size marble chips. This is why it is difficult to start a fire using large logs. It is easier to start the combustion reaction using small twigs, because the smaller particle size speeds up the reaction. For the same reason, in coal-fired power stations, the coal is first pulverized into a powder before it is combusted to produce heat. The concentration of reactant also influences the rate of reaction. The concentration refers to the amount of reactant molecules found within a space. If the concentration increases, there will be a higher number of molecules found in the space, and so the chance of those molecules colliding with other reactants has increased. We examined this through an experiment where magnesium was reacted with hydrochloric acid. We tried the reaction using 3 different concentrations of acid. The lowest concentration solution had not fully reacted after 1 hour. The magnesium fully reacted with the 1 molar acid in 3.5 minutes, and the magnesium had fully reacted with the 2 molar acid in 2.2 minutes. Given that the 0.5 molar solution did not produce a complete reaction, it is not valid to include that data point in the analysis. This only leaves 2 valid data points, which is not sufficient to fully describe the relationship between concentration and reaction time. It is only possible to see that increasing the concentration increases the speed of the reaction. We also examined this through another experiment where we used dilute potassium iodate and reacted this with a fixed amount of starch. The concentration of potassium iodate was varied from 10% to 90%. The time taken was plotted against the percentage concentration of potassium iodate. The results show that there was a logarithmic relationship between concentration and the time taken to react. Clearly, the higher concentration gives a faster rate of reaction. Going back to our example of a wood fire, we can see how the concentration of oxygen influences the rate of the combustion reaction. As the combustion occurs, the oxygen reacts with the wood, producing carbon dioxide. This reduces the concentration of oxygen in the air surrounding the fire. Fanning the fire blows away that air and replaces it with fresh air that has a higher concentration of oxygen. This higher concentration results in the rate of reaction increasing. Temperature also affects the rate of reaction. Temperature affects the particle energy and the particle velocity. When particles are moving faster, there is an increased chance of collision with other reactants. When these collisions occur, there must be enough energy in the collision to break any bonds in the reactants so that new bonds can be formed. The temperature affects this collision energy. This means that higher temperatures cause faster rates of reaction. This relationship was examined by acidifying sodium thiosulfate to form acid and solid sulfur. The time taken to become opaque was measured when the reactants were at a temperature of 22 degrees. We then repeated this at temperatures of 30 degrees, 40 degrees, and 60 degrees. The results showed that the time needed to react decreased as the temperature increased. An inverse power relationship can be seen in this reaction. We use a refrigerator to reduce the temperature of food to reduce the speed of reactions that cause the food to spoil. Another way to influence the rate of reaction is by using a catalyst. A catalyst is another substance involved in the reaction, but it is not a reactant because it does not get consumed in the reaction. The catalyst provides an alternate pathway for the reaction to take place. Instead of all the reactants needing to collide, some of the reactants can first react with the catalyst, and then the catalyst reacts with the other reactant. To examine this, we did a reaction of zinc and hydrochloric acid, and then repeated the reaction in the presence of copper, which acts as a catalyst. Without the copper catalyst, the reaction was completed in 5 minutes and 2 seconds. With the copper catalyst present, the reaction was completed slightly faster in 4 minutes and 54 seconds. This shows that by removing the catalyst, the reaction time is increased by almost 3%. One common use is in cars, where platinum is used as a catalyst to speed up the oxidation of poisonous carbon monoxide to produce the safer carbon dioxide. In conclusion, we conducted several experiments to explore the factors that influence the rate of reactions. We have found that the rate of reaction is influenced by the ability of reagents to come into contact with one another, and the energy of those reagents when they collide. In one experiment, we showed that solid reagents have a slower rate of reaction when they are placed in layers compared to when they are mixed together. This is because the mixing helps the reagents to collide faster. The rate of reaction increases further when the solids are dissolved, because this allows the reagents to become more mobile and move around to speed up the collisions. In another experiment, we saw that the size of the solid particles also influences how rapidly collisions between reagents occur. Crushing a reagent to decrease the particle size exposes more surface area of the reagents, and so speeds up the rate of collision. This speeds up the rate of reaction. We then looked at the concentration of reagents. We found that the higher concentrations resulted in faster reactions, because the chance of reagents colliding is increased when the concentration is higher. Temperature was also assessed, and we found that higher temperatures caused faster reactions because the reagents had higher energy. This energy increased the chance that the collisions would occur with enough energy to break the existing bonds in the reagents. Similarly, the presence of light was found to also influence some reactions. The light also adds energy to the reagents, and so increases the energy levels just like temperature. Finally, we looked at catalysts, and found that sometimes the presence of a catalyst provides an alternate pathway for a reaction to occur, and that this alternate can require less energy than the original pathway. This means that some reactions occur faster when a catalyst is present. The experiments were useful to find these general trends. However, there were some limitations. Some experiments did not have a sufficient number of data points to find clear mathematical relationships between the factors and the reaction rates. The first experiment that looked at concentration only yielded 2 valid data points, and so cannot be used to find a clear trend. Similarly, the experiment on light using silver bromide was qualitative in nature. It could be improved by measuring the amount of silver produced from the decomposition reaction. Overall, all experiments could be improved if we designed them to measure the actual rates of reaction over time. This would involve measuring the amounts of reagents and products in real time during the experiment. This sort of analysis would provide far greater detail in the analysis. We also could have added another experiment to test how atmospheric pressure would influence the rate of reaction.